Hello, this is section 5.1 for Calc survey, and today we're going to be talking about distance and accumulated change. So back in chapter 2, we did the calculus as a study of a function's rate of change. We computed the slope of the tangent line, which we called the derivative, and that was referred to as differential calculus. So all first semester, all the way up through chapter 4, we were doing differential calculus. Starting with chapter 5, we're going to transition to our new goal, which will be to work backwards, which is kind of interesting. And we're going to call this integral calculus. So we're going to kind of switch gears in a way, but we're still going to use all of that stuff we did through the first 4 chapters, and it's going to be very useful with what we're about to get into, okay? So here's an example. If a math tutor makes $45 per hour for 5 hours, how much has she made total? So now in your heads, you're thinking that's really easy. You just multiply 45 times 5. Okay, I agree. But now I want you to think of it a different way. So if you were to graph that $45 per hour, technically that's a derivative. That's a rate. It's a horizontal line of $45 at 45. Okay, that's our derivative graph. And for 5 hours, notice I made 5 tick marks here. So what shape did you just create? You created a rectangle. Oh, well, what's the area of a rectangle? Well, it's base times height. Oh, 5 times 45. So when you knew to multiply, you're technically also finding the area under your derivative graph. Isn't that cool? And if you notice the units, $45 per hour times hours, your hours cancel and you're left with just the dollar amount. So the area under the derivative, when we stop at the x-axis, will spit out the number of dollars that you've made during that 5-hour period. Okay, so we're going to build on that concept now. So what are some ways you can estimate the money earned given the following graph? So what if it's not just a horizontal line? Okay, so it's not a horizontal line. It's not even a straight line where we could maybe potentially use a triangle formula to find the area under that curve. So we're going to have to get a little creative. So maybe count the boxes underneath. We're trying to get the area under this curve. So, or maybe create shapes, geometric shapes. Maybe make this into a triangle here and maybe a trapezoid, rectangle. You have to get creative. Maybe the area of individual trapezoids. So if you kind of notice, you kind of have little individual trapezoids here. So we'll have to find ways to estimate the area under the curve. All right. Let's look at another one. So suppose you travel 20 miles per hour for 1 hour, 50 miles per hour for 3, and 60 miles per hour for half an hour. So I've kind of graphed that for us. What is the total distance traveled? All right, so you kind of see you've created 3 different rectangles that you're finding the area under of, but technically you are finding the area under those horizontal lines, okay? All right, so now you're given a table of data, and notice it's the velocity, it's your derivatives. These are the different velocities. So we went ahead and plotted those on our graph, and then we kind of connected them. It makes a nice little curve there. And we want to find, so the process of computing the total distance traveled is complicated in the situation where the velocity is not constant over given intervals, such as above. Use the table below to estimate the total distance traveled. Okay, so we plotted the points, and we're going to try to estimate the distance by finding the area under the curve. That's the whole idea. So what we did is we first did an underestimate. So we looked at each rectangle, and we're going to have to make the base 2 for each rectangle. Can you see how it goes up by 2's? So we're going to look at each individual rectangle, and to do an underestimate, we'll use the left side of each rectangle because it's an increasing function. So we're just going to use the left side to give us the height for each rectangle, and you stop when you get to the curve. The curve determines the height. So the height here looks like it's 10, and then the height here, it's going to be 44. That creates that rectangle. And the height here would be 70 and so forth. So you actually use 10, 44, 70, 88, 98, and then you stop. You don't want to use that last bit of data because that would give you an extra rectangle over here we don't want. So then you add all those areas together, and that's how we're getting 620 feet. And we know that's an underestimate. So then if we do an overestimate, well, the same first rectangle, but now we'll want to use the right side to determine the height. See how that gives an overestimate? Same thing here. You want to start, you use 4 to get that. So that's where these are coming from. Now, if you notice, you multiplied by 2 each time, so I went ahead and just put that out in front. That's the base length of each rectangle. Then we're adding the heights. So for the overestimate, we ended up using the right side. So if you want to start from the right and just not use the first set of data, you'll always be throwing out a set of data. Okay. But this at least gives us an underestimate and an overestimate. And of course, to get a better estimate, you just average those two together. So at least that's a way of finding the area under the curve. Okay. Especially with a table and you have to use the data in the table. All right, so here's another example. That's actually the same one. So let's look at the same data with smaller intervals of 1 second versus 2 seconds. So now you can see you're creating more rectangles. And we went from an underestimate of 620 and an over 802, and now our under is 670 and over is 761. So notice they're closer together because you're using more rectangles. You're using more data to get the area under the curve. Right? Now, eventually, if you keep adding more and more rectangles, the better estimate you're going to get, and that's the idea. So that's what it's saying on page 236. Visualize exactly what happens as the intervals get smaller and smaller. Okay. All right, so if the velocity is positive, the total distance traveled is the area under the curve. So we've already kind of discovered that. On a recent bicycle trip, on my velocity in meters per hour is represented by a function with time in hours. And that's nice because it's just a line. So I went ahead and graphed that. How far did I travel in 4 hours? All right. So I have the velocity graph. I can find the area under that. We say curve, even though it's a line, but we can find the area under that curve. And we notice it makes a trapezoid. So you can use the trapezoid formula, or if you happen to forget it, so this is the trapezoid formula, but if you happen to forget it, you could break it up into a triangle plus a rectangle. But this now tells me how far I traveled during that 4-hour period. Okay. All right, and then one more little example down here. So a jogger starts running from a statue in the park at noon. So when x equals 0, his rate in kilometers per hour is given below. Positive rates indicate the jogger's running west, and negative rates indicate the jogger's running east. Where is the jogger at 4:30? All right, so key thing is these represent the rates. So the area from the derivative graph here to the x-axis will tell us how far that runner has traveled. So we just kind of counted the squares on this. That's how we're getting these numbers. So we just said, well, that looks like roughly 3. And be careful. Notice this is a 2, whereas this is only 1. So watch out for stuff like that. And then same thing here. We just counted the squares and estimated 12. And it did say you're going east when it's below, west when you're above. So you can kind of see at noon, or say, excuse me, at 4:30, you can give an estimation of roughly 9 kilometers west of the statue. Okay. So you have to practice these rectangles. And don't get caught up on when it says underestimate, don't try to memorize that, well, when it's an increasing function, I want to use the left side of each rectangle and vice versa. It's not worth it. You can easily sketch out the function and decide, well, I want to use, looking at either side, which one's going to give me the lower estimate, and you can see that it's the left. So don't get caught up on which side of the rectangle you're going to use to give the estimation. Just follow the instructions and then just be careful. And if it does switch from increasing to decreasing, that will change which side of the rectangle you're going to pick. So you have to be a little bit careful with your over and underestimates. Some students do just fine with these rectangles. They see this as, well, this is really simple. Other students struggle. So you need to make sure you do the homework to see where you fall and if you need extra help or not, okay? But make sure you map out the data, In the next couple of sections, we're going to keep practicing this concept. So make sure you're staying on top of it and just email me, let me know if you have any questions. Thanks.